Okay, so Bismillah Rahman Rahim. We were discussing the direct measurement of consumptive use. So we already discussed the field experimental plots. The third method is soil moisture studies. This method is especially suitable to those areas where soil is fairly uniform and groundwater is deep enough so that it does not affect the fluctuations in soil moisture within the root zone of the soil. So this method, the soil moisture studies, is suitable for those areas where soil is fairly uniform and groundwater is deep enough so that it does not affect the fluctuations in soil moisture within the root zone of the soil. Soil moisture measurements are done before and after each irrigation. The quantity of water extracted per day from soil is computed for each period. A curve is drawn by plotting the rate of use against time, and from this curve seasonal use can be determined. So in this method, a curve is drawn by plotting the rate of use against the time, the quantity of water, the rate of use against time, and from this curve seasonal use can be determined. So here you can see that in soil moisture studies, we need to measure the soil moisture before and after irrigation. The fourth one is the integration method. In this method, it is necessary to know the division of the total area under irrigation, crops, natural vegetation, water surface area, and barren open land area. So the integration method is summation of the products of unit consumptive use for each crop times its area, means for the crops. Then we have unit consumptive use of native vegetation, any other vegetation that may be present, times its area, water surface evaporation times the water surface area, and evaporation from the bare land time its area. So you can see that in this method, the whole land area, the total area, that is divided into these different sections representing the crops, any natural vegetation, the water surface area, and the barren land. Thus, in this method, annual consumptive use for the whole of the area is found in acre feet or hectare meter units. So in this method, annual consumptive use for the whole of the area that is determined. The fifth method is inflow-outflow studies for large areas. So in this method also annual consumptive use is found for large areas. If U is the valley consumptive use, it is given by this equation. Now in this equation, all the terms, all the measurements, they will have the units of acre feet or hectare meter, because we simply add or subtract the different terms. So they must have the same units in order to add or subtract these quantities. So in this equation, U is the valley consumptive use in acre feet or hectare meter. I is the total inflow during the 12 months year. P is the yearly precipitation on valley floor. GS, that is the ground storage at the start beginning of the year. GE is the ground storage at the end of the year, and R is the yearly outflow. So this is like a water budget equation to calculate the annual consumptive use, and this is used for large areas. Next, we discuss consumptive use determination by use of equations. We have different equations are available to us that we can use to calculate the consumptive use. The first one is the Blaney-Kreidel equation. Now it states that monthly consumptive use is given by this equation, where Cu is the monthly consumptive use, K, that is the crop factor determined by experiments for each crop under the environmental conditions of the area. T is the mean monthly temperature in degree Celsius or centigrade. P is the monthly percent of annual daylight hours that occur during the period. So this is the Blaney-Kreidel equation. Cu, that is the monthly consumptive use, that is equal to K into P divided by 40 into 1.8 T, that is the mean monthly temperature, plus 32. Now let we consider this P by 40 is equal to F. This factor, let we take it as equal to F. Then it can be written as that Cu is equal to K times F. It was found that K was too low for the short periods between irrigations. So the formula was modified as like this: Cu is equal to K summation of F. And also, if K is variable, here we are assuming one value for K. If K is also variable, this formula can also be write down like this: Cu is equal to summation of K into F. Can be written in this form also. So where Cu is the seasonal consumptive use, that is consumptive use during the period of growth for a given crop in a given area. So using this equation, we can estimate the consumptive use or evapotranspiration for crops. Now in this equation, we have this K here. So this K, which is shown here, that it is the crop factor determined by experiments for each crop under the environmental conditions of that area, or there is a table available, monthly crop coefficient factor K, this is small k, for use in Blaney-Kreidel equation. So you can see here that we have rice. So value of K is 1.1 and a range of K, that is 0.85 to 1.3. Similarly, we have wheat, 0.65 value of K, the range is 0.5 to 0.75 and so on. So you can see that for different crops, the K values and ranges are given. So if we solve a problem and K value is not given, we can use this table to take the average value and use it in the equation to estimate the consumptive use. Similarly, in this equation here, this P is the monthly percent of annual daylight hours that occur during the period. So how to get its value? Again, we have this table available, monthly daytime sunshine percentage hours. This is P. That can be taken the value here for any location. This is, for example, for the north. It can be for the south also. So you can see here that 5 degree north, 10 degree clear. This is latitude in degrees here. So this shows the location of that area in the northern hemisphere. So for this location, for all the months, you can see from January to December here. So this is how the p value, monthly, daytime, sunshine percentage, hours. So we can pick the value from here that we put in the Blaney-Cradle equation to estimate the consumptive use for the crops. Let us solve a problem on this. We have this problem 2.9 from the book by Gerg. Wheat is to be grown at a certain place. The useful climatological conditions of which are tabulated below in the table. Determine the evapotranspiration, that is consumptive use, and the consumptive irrigation requirement of wheat crop. Also determine the field irrigation requirement if the water application efficiency, that is 80%. Make use of Blaney-Cradle equation. So now in this equation, this table is given. We have wheat that is to be grown at a certain place. So now the months are given. We have November, December, January, February. Monthly temperature in degrees Celsius or centigrade averaged over the last 5 years for these months are given. For month of November, 18 degree centigrade, then 15, and so on for the other months. Similarly, the p value is given here for this question. If we do not have these p value given to us, then we can use this table for any location. Clear, for example, 10 degree north, then for the different months we can pick the value of p from this table. But here in this question, the p values are given. So monthly percentage of daytime hour of the year computed from sunshine tables, which I already show you. And we have the useful rainfall in centimeter, that is averaged over the last 5 years. For these months, the useful rainfall, that is the effective rainfall, so that is also given. Now first we have to calculate the evapotranspiration or consumptive use. So we already know that according to the Blaney-Cradle equation, if we apply this equation here, so Cu, that is the consumptive use or evapotranspiration, that is equal to K, small k, into summation of F. And this F, that is given by P by 40 into 1.8 T plus 32. So what we can do is that now for the 4 months here, November, December, January, and February, we have to calculate this F. P is given and T is given. We have this is the temperature and this is the P. So we can calculate So we have November, December, January and February that we can write down here. November, December, January, and we have February. Now we can calculate this F for these months. So now what we can do is that for November, this T is 18. So T is equal to 18 for November. That is degree C. And what is P here? 7.20. So P is equal to 7.20. So now you put in the above equation here, and then we calculate the F value. So the F comes out to be 11.592. This is 11.592. Now next for December, we have the temperature as 15 and we have the P value as 7.15. So if you put in the above equation, this comes out to be 10.546. So this is equal to 10.546. Similarly, we go for temperature 13.5 and then P 7.30. So this is 10.275. And finally, we have the temperature is 14.5 and the P value 7.1. So F comes out to be 10.313. Now, what we have to do in this equation, that consumptive use is equal to K into summation of F. So it means that we have to calculate summation of F. You just add these values. So summation of F, that will be equal to just sum of all these values. So this is equal to 42.726. Now in this equation that we have that consumptive use Cu or evapotranspiration, this is equal to this small k into summation of F. So if k is not given in the question, you see that we have wheat. So we go back and you can see here that for wheat, this is now wheat from this table. This is wheat and we can consider the value of K is 0.65. So you can see that from table three eight for wheat, this small k, that is equal to 0.65. So we just take this value here, 0.65. Now we can put the values here and we can calculate Cu, the consumptive use or evapotranspiration. That will be equal to 0.65 into 42.726. So this will be equal to 27.77 centimeter. Cu is in centimeter. 27.77 centimeter. Clear? So this is how we calculate the consumptive use. Clear? Now after this, what it is required, we need to calculate the consumptive irrigation requirement. So consumptive irrigation requirement, that is CIR, that is actually equal to Cu, the consumptive use, minus the effective rainfall. So for this we need to calculate the effective rainfall for the 4 months. So in here we can calculate the effective rainfall. Just we need to add up all these values. 8.38 centimeter, 8.38 centimeter. Just we add up all these values. So we have consumptive use that we just calculated, 27.77 centimeter, and we have this effective rainfall that we just add 8.38 centimeter, 8.38 centimeter. So from here CIR, consumptive irrigation requirement, so that is equal to 19.39 centimeter. This is for the wheat crop. Also determine the field irrigation requirement. So the field irrigation requirement, that we just defined, that this is equal to net irrigation requirement divided by eta A, where eta A is the water application efficiency, that is given 80%. Now we have calculated consumptive irrigation requirement, but here we need to put the net irrigation requirement. What we can do is that we can consider this NIR, net irrigation requirement, is equal to consumptive irrigation requirement. And why we can consider this? Since no water is used for deep percolation, since no water is used for deep percolation. So now what we can do here is that we take it as 19.39, and we have the water application efficiency as 80%, so 0.80. So we have this field irrigation requirement, 24.24 centimeter. So the field irrigation requirement, that is 24.24 centimeter. The second method, we have Hargreaves class A pane evaporation. In this method, evapotranspiration, that is consumptive use, is related to pane evaporation by a constant K. Now this is capital K. In the previous equation we use small k, this is now capital K. So ET, evapotranspiration or consumptive use, that will be equal to K times EP, where ET is the evapotranspiration or Cu is the consumptive use, EP is the pane evaporation, and K is the consumptive use coefficient. So this is exactly similar to, if you remember, you studied in hydrology to estimate the evaporation from a water body. So there you use Kp, the pane coefficient. Clear? So this is the same concept here. Consumptive use coefficient is different for different crops and is different for the same crop at different places. It also varies with the crop growth and is different at different crop stages for the same crop. So in the absence of local figures for specific crops, the data given in table 313, here this is table 313, we have for different crops percent of the crop growing season from 0 to 100%. This is the percent of the crop growing season, 0 to 100% for different types of crops. We can assume the or take the value of K from this table if it is not calculated for the local conditions. So the data given in table 3.13 recommended by Hargreaves can be used, and in this table actually the crops, they have been divided into these 8 groups. So we have group A, B, C, D, E, F, G, and the 8th group that contains paddy or rice. So in group A we have potato, cotton, maize, beans, etc. In the group B we have tomato, olive, plumes. In group C we have onions, grapes, melons, carrots. Group D we have wheat, barley, etc. Group E we have pastures, other orchard crops, etc. These are the different crops. Group F we have oranges, fruits. Group G contains sugar cane, alfalfa, and the 8th group, that is rice. So different crops are divided into different groups. These are total 8 groups, and then for these 8 groups, that is, you can see here group A, group B, group C, group D, group E, F, G, and we have rice. So for different percent of the growing season from 0 to 100%, these K values that can be taken from here in estimating the consumptive use or evapotranspiration. Class A pane evaporation measurement. This EP, it can be experimentally determined by directly measuring the quantity of water evaporated from the standard class A pane. So the standard class A pane, this pane is 1.2 meter in diameter, 25 centimeter deep, and bottom is raised 15 centimeter above the ground surface. So you can see here that the standard class A pane, you might have studied in hydrology also. This is a pane 1.2 meter in diameter, and it is 25 centimeter deep, and the bottom that is raised 15 centimeter above the ground in order to avoid any effect of the conduction of the ground on this pane. The depth of water is to be kept in a fixed range such that the water surface is at least 5 centimeter and never more than 7.5 centimeter below the top of the pane. You can see here 50 to 75 millimeter from the rim, from the top. So the water evaporates, and then the depth of water that is calculated. So this is how we can estimate the EP. This is another picture. You can see that sometimes we place the anemometer here to measure the wind speed also. The pane evaporation EP can also be determined by using the Christensen formula. So this is a formula with the help of which we can also calculate the pane evaporation. So this formula is EP is equal to 0.49 R into these coefficients CT, CW, CH, CS, and CE. So in this equation, this EP is the pane evaporation, R is the extraterrestrial radiation in the same units as EP in centimeter or millimeter. CT is the coefficient of temperature that can be calculated using this equation if we know the mean temperature. CW, that is the coefficient of wind velocity. It can be calculated from this equation, this coefficient, where W is the mean wind velocity at 0.5 meter above the ground in kilometer per day. CH, that is the coefficient of relative humidity, can be calculated from this equation, where H is the mean percentage relative humidity at noon or average relative humidity for 11 and 18 hours. CS, so that is the coefficient of percent of possible sunshine, can be calculated from this equation, where S is the mean sunshine percentage, and CE, that is the coefficient of elevation. So where E is the elevation in 100 meters, we can estimate this coefficient for any area if we know its elevation. So this is the Christensen formula, which can also be used to determine the pane evaporation. The third method that is important, that is known as the Penman equation. So Penman developed a theoretical formula based on principles of both energy budget and mass transfer approaches to compute potential evapotranspiration in the following form. Potential evapotranspiration that we defined earlier. So this Penman equation you might have studied in hydrology also when you study the chapter of evaporation. So there we have different methods in order to estimate the evaporation from a water body. So Penman developed this theoretical formula based on the principles of both energy budget method, where we consider the energy budget of the water body to calculate the evaporation, and the mass transfer approaches. Clear? So he combined these two techniques to compute potential evapotranspiration in this form. This is the Penman equation. In this equation, ET, evapotranspiration, that is equal to A into H plus alpha into E sub A divided by A plus alpha. So ET, that is the evapotranspiration in millimeter per day. We have this alpha, this is the psychrometric constant, its value is known to us, 0.49 millimeter mercury per degree centigrade or Celsius. A in this equation, this is the slope of the curve between the saturated vapor pressure and temperature at mean air temperature. EA, that is the drying power of air, which includes wind velocity and saturation deficit. Saturation deficit, that is the difference between the saturation vapor pressure and actual vapor pressure, and is given by this equation. EA is equal to 0.002187 into 160 plus U2 into ES minus EA. So 0.002187, this U2, this is actually the mean wind speed in kilometer per day measured 2 meter above the ground. This ES and EA, these are the saturation vapor pressure at mean air temperature, and EA is the actual vapor pressure in the air in millimeter of mercury, and is equal to ES multiplied by relative humidity. So if we know the relative humidity, RH, that is the relative humidity, so we can multiply with saturation vapor pressure to calculate the actual vapor pressure. And in this equation, we have H. So this H is the daily net radiation in millimeter of water given by this equation. H can be calculated using this equation, where Ra is the mean monthly extraterrestrial radiation in millimeter of water per day. This phi here, this shows the latitude of the place where ET, evapotranspiration, is being computed. R, small r, you can see here this small r. So this is the reflection coefficient of the surface. So these guideline values are given, 0.15 to 0.25 for close crops. For barren land, it is 0.5 to 0.45, and for water surface, it is 0.05. Similarly, in this equation, this small n here, you can see this small n here, and also it is here. So this is the actual duration of bright sunshine, which is a function of latitude of the place and is observed data at that place. If we do not have the values for this small n, alternatively it can be taken equal to P. Earlier that the table was available for P, so we can take this n as equal to P. capital N, that is the maximum possible hours of bright sunshine available at different locations. And in this equation we have this sigma. So this is the Stephen Boltzmann constant. Its value is 2.01 into 10 power minus 9 millimeter per day, and Ta, that is the mean air temperature. Now the wind speed that we have to include here, you see, at 2 meter U2, wind speed in kilometer per day measured 2 meter above the ground. So if the wind speed is measured at any other height, can be reduced to 2 meter height by the relationship. This is the formula available. So this is the wind speed at any height z. It can be reduced to u2, the wind speed at 2 meter above the ground here. So these are the different parameters in the Penman equation. These are the tables available from where we can pick the values. This is the table for saturation vapor pressure. This is table 310, and these tables are taken from the book Irrigation and Water Power Engineering by Pumia. So you can see here that in this table we have this temperature. So for the given temperature, we can read the saturation vapor pressure and the slope of plot between 1 and 2. Means the slope of the plot between the temperature and between the saturation vapor pressure. So this is actually this A here. You see, in the equation we have this A, slope of the curve between saturation vapor pressure and temperature. So from this table, this is actually A in the Penman equation. Similarly, we have this table 311, mean monthly solar radiation RA, that we can take for the months. It's from January to December, and we have the northern hemisphere, we have the southern hemisphere for different locations. Clear, for the given months we can read the value of RA. So this is the mean monthly solar radiation incident on Earth outer space, that is the extraterrestrial radiation in millimeter of evaporable water per day. Similarly, we have another table, table 3.12. We have maximum possible hours of bright sunshine in hours. This is the capital N. So we have the north latitude in degrees. This we can use because Pakistan is in the northern hemisphere. We can have this table for the south latitude in degrees. So we have this latitude in degrees and we have these months. So from this table we can pick maximum possible hours of bright sunshine in hours. And this is P, the small n, that is given in the formula here, the actual duration of bright sunshine, which is a function of the latitude of any area. Alternatively, if it is not given, alternatively it can be taken as equal to P. So in this here table 3.9, this can be taken as equal to small n. So we have the latitude and we have for the months for the any specific location on the surface of Earth. We can pick the value of small n from here. Now let us try to solve a problem how we apply the Penman's formula and use these different tables to calculate the consumptive use. So this is example 3.19 from the Pumia book. Calculate the consumptive use or evapotranspiration of rice for the month of January by using the Penman's formula for the following data available at the field. So latitude of the place is 20° north, northern hemisphere. We have mean monthly temperature, that is 15 degrees centigrade or Celsius. Relative humidity in January for that place, that is 50%. Elevation of the area, that is 250 meter, and wind velocity at 2 meter height, that is measured as 25 kilometer per day. So now we already know that we have to use the Penman equation. So that is equal to ET, the evapotranspiration, and this is given as A into H. We have to now calculate the values for these different parameters, plus we have alpha into EA divided by A plus alpha. So now we have to use this equation, but as we discussed in the previous slides, now we have to calculate the values for these different parameters. So let us go and proceed step by step for this solution. So we are given the temperature. So for the mean temperature, that is 15° centigrade or Celsius, we go to table 310. So you can see here, first we go to this table 310, and now we are given the temperature 15° centigrade. This is temperature in centigrade. We have this 15° centigrade that is given in the question. So we can read the value of saturation vapor pressure ES from here, 12.79. This is the value for ES, saturation vapor pressure, 12.79 millimeter of mercury, and also the value for this A, slope between the temperature and the saturation vapor pressure. So the value for A, that is also given from here, 0.80. So these two values we can pick. Clear, for the given temperature of 15° centigrade. So from table three point 10, for the temperature of 15° C, we read the values, that is the saturation vapor pressure ES, that is equal to 12.79 millimeter of mercury, and we also read the value for the slope. So that is A is equal to 0.80. clear, 0.80. So this value of A, this is actually used in this formula here, A, in the numerator and in the denominator. Now next we have from table from table 311, what we can pick the value. So you see that the latitude is given as 20° N, and we have the month is January. So we go to table 311. You can see this is table 311. Now we have the month of January. This is the month of January, and we have location of that area is 20°. This is given in the question, 20°. 20°, and month of January, so this is 10.8. This value we pick. This is RA, mean monthly solar radiation, clear, in millimeter of evaporable water per day, 10.8. So this value we pick from the table, that is RA. This is equal to 10.8 millimeter of water per day. This is for the latitude of 20° and in the month of January. Next we have from table 3.9. So we have from table 3.9. So in table 3.9, what we have, this is table 3.9, and we can estimate the value of the small n, that is taken as equal to P. So we have the latitude. So the latitude, that is equal to, how much is the latitude here, 20° N. So this is the north, and we have this 20° here. And for the month of January, this is the value of small n, 7.74. So we have this small n, that is taken as equal to P. So this is equal to 7.74 hours. This is for January, and latitude of place 20° N. Now we have this table 3.12 also. We have from table 3.12. From there, what we can read, again we have table 3.12 here. So we can read the value of the capital N, which is the maximum possible hours of bright sunshine. So in this table for latitude 20 degree, we have this latitude 20 degree, north latitude in degrees, and we have month of January. So this is the month of January here. This is now the value that we will pick. This is 11.1. This is capital N. So we have this capital N, that is equal to 11.1 hours. So now we have taken these values from the different tables. Now what we can do is we can calculate this n, small n divided by capital N, because if I go back and see the formulas, you see that I need to calculate this small n by capital N, small n by capital N. So we can calculate these ratios. So this will be equal to 7.74 divided by 11.1. So this will be equal to 0.697, 0.697. Next we can calculate this EA, the actual vapor pressure. The saturation vapor pressure we have already calculated from this table 310. We have taken its value 12.79. So the actual vapor pressure, this will be equal to saturation vapor pressure multiplied by the relative humidity, RH. Now in the question it is given relative humidity in January, that is 50%. So we can put its value here, ES, that is 12.79 12.79 into 0.5. So the actual vapor pressure, this is 6.395 millimeter of mercury, Hg, hydrogarium. Next we have to calculate this EA. So EA is here in this equation here, EA, and EA is given by this equation here. So EA, that is equal to 0.002187 into 160 plus U2 into ES minus EA. This is the equation. So if you put the values, just plug in the values for all the parameters, and this will be equal to 2.59 millimeter per day. Next we have rice. This is given in the question. This crop is rice. We have to estimate the value of the small r. Clear? This small r here. So this small r here, this is the reflection coefficient of the surface. So because rice, you can see here for close crops, it can be between 0.15 to 0.25. So we can assume the value from that range. For rice, we have this as a close crop. So we can assume the value of small r is equal to 0.20. Next we have the alpha. So alpha, we already know that the value of alpha psychrometric constant, that is 0.49, 0.49 millimeter of mercury Hg per degree C. These are constant. Clear? In the equation we already discussed them here. This alpha psychrometric constant 0.49, and we have the sigma here, Stephen Boltzmann's constant. This value is already known to us. So we have this sigma that is equal to 2.01 into 10 power minus 9 millimeter per day. So now we can estimate the value of H, the capital H here, that is given by this equation here, this equation. H we can estimate now in here. So this H value comes out to be 2.14 millimeter of water per day. Now in the equation, that is ET, evapotranspiration. So this is equal to A into H. We have calculated all the values, plus alpha into EA divided by A plus alpha. So in this formula, we can put the values. So this is 0.8 into H, that is 2.14, plus we have alpha, that is 0.49, into EA 2.59, divided by A, that is 0.8, plus alpha, that is 0.49. So from here we can calculate this ET, evapotranspiration. This comes out to be 2.31 millimeter per day. Now in the question, it is asked that you compute the consumptive use for rice for the month of January. So for January, we have this ET that is equal to 2.31 millimeter per day, and we have 31 days in the month of January. So this day cancel out, and we have this ET that is equal to 71.64 millimeter of water for January. So this is how we apply the Perman equation to estimate the evapotranspiration.